Hello everyone. We will see the solutions for UGC NET Electronic Science question paper for the examination held on 21st August 2024. First question: for a standard telephone circuit with signal to noise ratio of 1000 and bandwidth of 2.7 kHz, the Shannon limit for information capacity approximately is given. Signal to noise ratio 1000, given bandwidth 2.7 kilohertz. The channel capacity C, as per Shannon-Hartley theorem, is C is equal to bandwidth. Capacity C is equal to bandwidth log base to 1 plus signal to noise ratio. So bandwidth is 2.7 kilo log to 1 plus 1000, and its value is 9.9672. So 2.7 into 10 cube into 9.9672. So that is 26.9115 kbps, approximately 26.9 kbps. This is a capacity C, kilobits per second. Second question: a 6-bit digital to analog converter has a step size of 50 millivolts. We need to calculate full scale output voltage and percentage resolution. Given 6-bit digital to analog converter. So if it is 6-bit means total number of steps that is 2 power n minus 1. So that is 2 power 6 minus 1. Total number of steps is 63. Given step size 50 millivolts. Full scale output voltage VFS. Full scale output voltage VFS is total number of steps multiplied by step size. So that is 63 into 50 milli is 10 power minus 3 volts. 3.15 volts. Next is percentage resolution. The formula for percentage resolution is 1 by 2 power n minus 1 into 100, 1 by 2 power 6 minus 1 into 100, 1 by 63 into 100. So its value is 1.587 percentage. So correct option is 4. Next question: arrange the following logic families in increasing order of their noise margin. So noise margin is, it is defined as maximum noise signal that can be added to the input of a digital circuit without causing an undesirable change in the circuit output. The noise margin for TTL logic family, transistor logic family, is 0.4 volts, and noise margin for emitter coupled logic ECL is 0.3 volts. This is A. B. Next, noise margin for metal oxide semiconductor logic is 1.5 volts, and integrated injection logic noise margin is 0.35 volts. D. So they asked us to arrange in increasing order. So least value is for ECL. Next, integrated injection logic followed by transistor logic, and finally highest for mass. So that is B, D, A, and then C. B, D, A, C. Option 1. Next question. The band gap of semiconductor material that can be considered for making the solar cell will be. So generally, the ideal band gap for solar cell material is 1 point. Solar cell materials in between 1.1 electron volts to is in between 1.1 electron volts to 1.5 electron volts. So examples are gallium arsenide 1.42 electron volts, cadmium telluride CD cadmium telluride 1.44 electron volts. The solar cell made from cadmium telluride has a bandgap energy of 1.44 electron volts. The solar cell made from gallium arsenide has a bandgap energy of 1.42 electron volts. So the correct option is it lies between 1 and 2 electron volts. So some key points regarding solar cell is, so the principle of operation is photovoltaic effect. Solar cell works on the principle of photovoltaic effect, and nickel cadmium cells are rechargeable cells used in satellites. Next question. An operational amplifier as shown below has poor open loop gain of 45 AOL. It is 45, but otherwise it is ideal. Find the closed loop gain of an amplifier. Closed loop gain of an amplifier. So generally, for an ideal operational amplifier, open loop gain depends only on external resistors. So that is closed loop gain formula ACL is equal to 1 plus RF by RL. So closed loop gain depends only on external resistors. For ideal op amp, open loop gain is very high. So ideally it is infinity. So in that case, closed loop gain depends only on external resistors, where RF is a feedback resistor. RF by R1. RF is feedback resistor. R1 is the resistor at the input. Resistor at input. This is ideal operational amplifier case. But for non-ideal operational amplifier, where open loop gain is very low value, in that case, closed loop gain is given as ACL is equal to output voltage by input voltage, that is open loop gain AOL by 1 plus open loop gain into beta. Beta is feedback factor, feedback ratio. Its value is 5K by 5k plus 20 kilo ohm. So feedback ratio beta value is 1.5. Now closed loop gain ACL is equal to 45 by 1 plus 45 into 1 by 9. Sorry, 1 by 5. By 5. So its value is 45 by 10, 4.5. If suppose given the operational amplifier is ideal whose open loop gain is infinity, in that case closed loop gain depends only on external resistors. The closed loop gain is 1 plus RF 20 kilo ohm by input resistor 5 kilo ohm. So that is 1 plus 4. Its value is 5. So ideal op amp closed loop gain is higher when compared to the closed loop gain of practical amplifier. So now correct value is 4 point. Correct option is 4.5. That is option 3. Next question. Comparison of open loop and closed loop control systems. So open loop control system, closed loop control system. In open loop control system, the control action is independent of system output. But in case of closed loop control system, the control action depends on system output. Open loop control systems are simple and easy to construct. No stability problem here. These are stable systems. No stability problem. Open loop control systems are more stable and open loop control systems are more inaccurate and unreliable, whereas closed loop control systems are more accurate and reliable. These are complex to construct. Complex design is complex. Next, difficult to construct. This reliability and accuracy is due to feedback in closed loop control systems. Due to feedback mechanism involved in closed loop control systems, these are more accurate and reliable. Next point is closed loop control systems are optimized because they have ability to self correct, because they have capability to self correct, whereas closed loop control systems cannot be optimized. Let us see one by one statements. Statement A: open loop control systems are more stable in comparison with closed loop control systems. Correct. Open loop control systems are more reliable. These are not reliable when compared to closed loop control systems. It is wrong. Open loop control systems are easy to build in comparison with closed loop control systems because there is no feedback in open loop control systems. Very fewer number of components. Our statement C is correct. Open loop control systems can be optimized. Wrong. Open loop control systems cannot be optimized, but closed loop control systems can be optimized. So the correct statements are A and C. The correct option is 3. Next question. A coil draws 0.5 ampere current from 120 volt source operating at 60 Hz at zero point 0.7 lagging power factor. So they have given lagging power factor. So lagging means current lags behind applied voltage. So the element is inductor. Inductor has lagging power factor. The element is inductor. So if this is not a, if this is a, in case if inductor has, the coil has some resistance, resistance is also included. So R is the resistance, XL is the inductive reactance of coil. Now total impedance Z is equal to R plus J XL ohms. XL is inductive reactance, inductive reactance of coil. The element is inductor or simply coil. Next, R is a resistance. No. So in the question they have given cos phi 0.7. Phi is a power factor angle. That is cos inverse of 0.7. The phi value is 45.573 degrees. No. Resistance R is equal to mod Z cos phi. Similarly, inductive reactance XL is mod Z sin phi. Now, what is impedance Z? Impedance Z is magnitude of impedance is magnitude of voltage with respect to magnitude of current. So given voltage is 120 volts and current is 0.5 amperes. Now impedance is 240 ohms. Magnitude of impedance is 240 ohms. Now R is equal to mod Z cos phi 240 into 0.7. So that is resistance value is 168 ohm and inductive reactance XL. Inductive reactance XL is 240 into sin 45.573. So that is 240 into 0.7141. Its value is 171.4 ohm. This is inductive reactance. R is a resistance. We know mod XL is inductive reactance XL is j omega L. Apply modulus on both sides. Mod XL is modulus of j omega L. J is a complex operator. It will become omega L. Omega is angular frequency. In terms of linear frequency, 2 pi f into inductance L. Given frequency is f is equal to 60 Hz. Frequency of source. Now XL value is 171.4 is equal to omega, that is 2 pi f. Frequency is 60 and value is L. Inductor is L. Now inductor L value is 171.4 by 120 pi. Inductance L is 0.4509. The correct no coil resistance is 240 ohms. Correct option is 2 C. Coil resistance is 240 ohms. Wrong. Coil resistance is 168 ohms. Statement A. Wrong. Power factor angle is cos inverse 0.7. Power factor angle is cos inverse 0.7 is correct. Coil impedance Z is equal to R plus J omega L, that is Z is equal to resistance 168 ohms. Statement B is correct. 168 ohm plus J XL. What is XL value is 171.4 ohms. That is 168 plus J 171.4 ohm. Statement C is correct. Next, power factor angle is 32 degrees. It is wrong. Power factor angle is 45 degrees. Next, coil inductance is 0.45 Henry. Coil inductor is 0.45 Henry. Statement E is correct. Statement B, C, E are correct. As per options, the correct, as per A, B wrong, C, E correct. Three statements are correct. B, C, and E. The correct option is 2. C and E. Next question. A piezoelectric transducer having a wafer of piezoelectric crystal material with a relative permittivity of 700 is sandwiched between two plated electrodes, and the dimensions of electrodes is given 5 mm by 5 mm and thickness is 2 mm. When force of 10 Newton is applied, the piezoelectric transducer produces an output voltage of 40 volts. The respective value of its voltage sensitivity and charge sensitivity. Given output voltage V naught is 40 volts, force applied is 10 newtons, plate area dimensions, so that is 5 mm by 5 mm, and thickness T is 2 millimeter thickness, and relative permittivity epsilon r is 700, epsilon naught is permittivity of free space, that is 8.854 10 power minus 12 farad per meter. They asked voltage sensitivity of piezoelectric transducer. So that is voltage sensitivity of piezoelectric transducer. G is output voltage V naught thickness into pressure. So pressure is force per unit area 10 newtons. Area is 25 into 10 power minus 6. This is force per unit area, that is pressure. Next, voltage sensitivity G. Voltage sensitivity G is equal to output voltage by thickness into pressure. Voltmeter per Newton. Units is voltmeter per Newton. So that is output voltage 40, thickness 2 mm, 2 into 10 power minus 3, pressure is 10 by 25 into 10 power minus 6. Upon calculation, its value is 50 into 10 power minus 3. Voltage sensitivity G is equal to 0.05 voltmeter per Newton. 0.05 voltmeter per Newton. There are two options, 2 and 4. Next is charge sensitivity. Charge sensitivity D is equal to epsilon permittivity into voltage sensitivity G. So epsilon naught epsilon r into G voltage sensitivity. So epsilon naught is 8.854 into 10 power minus 12. Epsilon r value given 700. Permittivity, relative permittivity is 700, and voltage sensitivity is 0.05. So upon calculation, its value is 309.89 pico. So its value is 10 power minus 12 coulomb per Newton. So that is 309.8 approximately pico coulomb per Newton. 309.8. So option 2 is correct. Next question. For a given circuit, maximum power delivered to the load shall be. For maximum power transfer, according to maximum power transfer theorem, for maximum power transfer, the load impedance ZL is equal to complex conjugate of source impedance ZS. So that is given as per circuit. ZL is RL and ZS is RTH. For maximum power transfer to the load impedance RL must be equal to RTH. Now current in the circuit, let I be the current. The current in the circuit I is equal to voltage by total resistance RTH plus RL, but RTH is equal to RL for maximum power transfer. So that is VTH by 2 times of RL. So power is I square into output power I square into RL. So that is VTH by 2RL whole square into load resistance. So VTH square by 4RL is a maximum power that can be transferred to the load. VTH square by 4RL, option 3. Next question. For a silicon controlled rectifier, the I square T rating of an SCR represents the capability to withstand the overload current for a specific time, where I is a RMS value of current. I is a instantaneous value of current. Statement A is wrong. The square of current I over time T, I square T rating represents its capability to withstand the overload current for a specific amount of time without being damaged, where I is the instantaneous current, T is the time period. Next statement B. The negative gate bias decreases the forward blocking capability and minimize the false triggering possibility during high dV by dt operation. Statement B is incorrect. The negative gate bias applied to SCR can decrease the forward blocking capability, reducing reducing the effectiveness of device internal junctions in maintaining a blocking state, and negative gate bias minimize the risk of false triggering during high dV by dt conditions. Next statement 3. Resistance at the gate of SCR increases its dV by dt capability. Increasing the resistance at the gate of SCR increases the turn on time, so thereby reducing the turn off time. Statement C is correct. Next, the gate non-trigger voltage is the maximum DC gate voltage that may be applied between gate and anode, gate and cathode. So this statement D is wrong. In SCR, the non-trigger voltage refers to maximum DC gate to cathode voltage that may be applied while device is in its rated blocking state and still not cause SCR to trigger or turn on. Next, statement E. Inter- the turn-off time becomes shorter due to introduction of gold atoms in silicon, which serve as a trap for carriers, but it increases the on-state losses. Correct. Introduction of gold in SCR reduces the carrier lifetime, leading to shorter turn-off time because the gold serves as a trap for the charge carriers. Hence, switching performance is enhanced. It is used in high-frequency applications. The introduction of gold increases the on-state losses because of its more carrier recombination during conduction, leading to high power dissipation and reduced efficiency in on-state. The introduction of gold in SCR has advantage as well as disadvantage. Advantage is high frequency. It is used in high frequency operations, and disadvantage is it leads to power dissipation, thereby reducing the efficiency in on-state. So statement C and E are correct. So option 4. Next question. Segregation coefficient K. Segregation coefficient K. So it is defined as the ratio of concentration of an element in solid phase to concentration of element in liquid phase. K is equal to concentration of element in solid phase, concentration of element in by concentration of element in liquid phase. If K less than 1, elements tends to concentrate more in liquid phase. If K greater than 1, elements stays in solid phase as material solidifies. If K is equal to 1, element distributes evenly between solid and liquid phases. This segregation coefficient K quantifies how much element quantifies how much element concentrates in one phase relative to other. Or otherwise we can say K less than 1 is means solute is more soluble in liquid phase. K greater than 1 means solute is more soluble in solid phase. K is equal to 1 means solute has similar affinity of both phases. So this segregation coefficient for aluminum is 0.0029, so that is approximately 0.003. For arsenic, the segregation coefficient is 0.3. For boron, segregation coefficient is 0.8. For carbon, it is 0.07. For phosphorus, it is 0.35. Now, correct option is second one. The segregation coefficient of aluminum, it is very lower, so that is 0.003, less than carbon 0.07, less than boron. Sorry. So next is arsenic 0.3, less than phosphorus 0.35, less than boron 0.8. So boron has more segregation coefficient in this comparison table, and aluminum has least. The correct option is 2. Next question. 8051 microcontroller modes, regarding the modes of operation. So mode 0 operation is 8-bit timer with 5-bit prescaler. So that is 8-bit timer with 5-bit prescaler. It is 13-bit timer or counter. 13-bit timer or counter. So mode 0, 13-bit timer or counter. Option A is 3. Next, mode 1 is 16-bit timer or counter. Mode 1 operation is 16-bit timer or counter. So that is D is 1, A is 3, D 1. Next, mode 2 operation is 8-bit auto reload timer or counter. Mode 2 is 8-bit auto reload timer or counter. That is for C, the matching is 4. And mode 3 is, it is different for timer 0 and timer 1. For timer 0, working in mode 3 is used as 8-bit timer or counter. For timer 1, it is configured in one of the mode 0 or mode 1 or mode 2. So D is matching is 2. The correct option is 4. A3, B1, C4, D2. Next question. So given series RLC circuit with source voltage of 1 volt, resistance 10 ohm, and then capacitance is 12.5 microfarad, and resistance inductance L is 5 millihenry, and source voltage is 1 volt. So the given circuit is series RLC circuit. So the total impedance here Z is R plus JXL minus JXC, where XL is inductive reactance, that is omega L, XC is capacitive reactance, that is 1 by omega C. Units of impedance is ohms. At resonance, so now the resonant frequency. So we know that for series RLC circuit, impedance is minimum at resonance. At resonance, XL is equal to XC, that is omega L is equal to 1 by omega C. Magnitude of XL is equal to XC. So omega square is equal to 1 by L C. L value is 5 millihenry, 5 into 10 power minus 3, 12.5 into 10 power minus 6, 125, 10 power minus 10. So 125 into 5 is 625, 10 power minus 10. This is omega square. So from this, omega is 1 by 25 into 10 power minus 5, that is 10 power 5, 10 cube, 4, 100 by 25, that is 4 kilo hertz. So this is resonant frequency. So resonant frequency is 4 kilo hertz. So resonant frequency XL is equal to XC. At resonant frequency, impedance Z is at resonant frequency, impedance Z is minimum, and the minimum value is R. It is equal to only resistance. Below resonant frequency, so that is below omega naught, impedance Z increases as frequency decreases. So as frequency is decreasing, impedance value is increasing, and the dominating is capacitive reactance is more dominating. Above resonant frequency, again impedance Z increases as frequency increases. So as frequency increases above the resonant frequency, the impedance value Z is increasing. Below resonant frequency, as frequency decreases, impedance is increasing, and the impedance is minimum at resonant frequency. So now, so this is, so resonant frequency is 4 kilohertz. From the given options, 4.4k, 4.8k. So this is uh, B. 4.4k is D. 4.8k is A, and 3.2k is C. Here impedance is minimum. From here onwards impedance increases. From here onwards impedance gets increased. Now the correct option is C, A, D and B. So in descending order, so least impedance at resonant frequency, that is 4 kilohertz. So 4 kilohertz is B. So B is a lower value, and highest value is the frequency value which is far away from least value is at B, and next close to the frequency which is close to resonant frequency is 4.4k, that is D, and impedance at 3.2k and impedance at 4.8k frequency it is same, so it is either AC or CA. AC D B or CA D B. CA D B. From the given options, CA D B is a correct thing. So option 2 is a correct. Next question. So the statements related to avalanche photodiode and pin diode. So PIN photodiode and avalanche photodiode. So PIN photodiode, so it has P plus region, intrinsic region and N plus region. In avalanche photodiode, it has N plus P intrinsic and then P plus region. So a lightly doped, in this pin diode, a lightly doped intrinsic region is sandwiched, intrinsic semiconductor is sandwiched between highly doped P region and N region. And pin diode doesn't have high intensity electric field. There is no high intensity electric field in the intrinsic region. But in case of avalanche photodiode, it works on the principle of impact ionization. It provides internal gain, and APD has, due to impact ionization, it provides internal gain for the current, and APD has, avalanche photodiode has high intensity electric field in the intrinsic region. This pin diode has lower noise level, it exhibits lower noise levels, but due to internal gain here, Due to impact ionization, here noise is relatively more when compared to our PIN diode. The response time of PIN diode is lower. Response time of PIN diode is low because of high resistivity intrinsic region. Next, the photocurrent, the response time it is lower here. Here the response time is more. Response time is lower and response time is more. Next, here photocurrent IP is equal to Q into Ne. Q is charge of electron, total number of electrons. Here photocurrent IP is Q N E with multiplication factor M. APD is more sensitive to single photon compared to photodiode. It is more sensitive. Avalanche photodiode is more sensitive. Next, APD is more sensitive to PIN diode. Statement A is correct. APD is a PIN structure. B is incorrect. A high electric field intensity is required in avalanche photodiode. Correct. There is less noise generation in APD. More noise generation in APD. Statement A, statement C are correct. AC correct. Option 4. Next question. It is related to 8051 microcontroller. So when 8051 is reset, what is the value of stack pointer? 8051 stack pointer is a 8051 stack pointer is 8-bit register, that points the last stored location in the system stack. 8051 stack pointer is 8-bit register that points to the last stored location in the system stack. So the stack pointer purpose is to access the stack. Its value range is 00 to FFH and initial value is 07H when 8051 is powered on. So 07H when 8051 is powered on. The stack pointer is initialized to the value 07H when 8051 microcontroller is reset, and stack can be stored and data can be stored to stack from 8008H onwards. It is incremented by 1 when data is pushed onto the stack. Next question. A silicon sample, it is doped with 10 power 10 arsenic atoms per centimeter cube. So given sample is doped with arsenic, nitrogen, phosphorus, arsenic, antimony and bismuth. All these are fifth group elements. When silicon is doped with fifth group elements, in fifth group elements, electrons are majority carriers. Electrons are more when compared to the holes. Electrons are majority carriers. When silicon is doped with arsenic, so it leads to the formation of N-type semiconductor. For an N-type semiconductor, electron concentration approximately equal to donor concentration. So therefore, whole concentration P naught is equal to intrinsic concentration square by donor concentration, or electron concentration N naught. This electron concentration N naught approximately equal to donor concentration, that is square of intrinsic concentration divided by donor concentration. Given intrinsic concentration is 1.5 into 10 power 10 atoms per centimeter cube. Donor concentration is 10 power 10 atoms per centimeter cube. Its value is 2.25 10 power 10 atoms per centimeter cube. So statement option 2 is the correct. Next question. The operating point of the transistor in the circuit. Given fixed bias circuit. So this circuit is fixed bias. They ask to calculate the operating point or Q point or quiescent point or operating point or bias point. Is a steady state DC voltage and DC current level at the transistor terminal when no input is applied. So we need to calculate the Q point or bias point. So given VCC is 10 volts, KVL at input side, as well as KVL at output side. So this is input side and this is output side. Emitter is connected to ground and this is collector, base terminal. This is NPN transistor. Arrow is pointing away from the base. It is an NPN transistor. Write KVL at input, KVL at output. So consider KVL at input side. Applied voltage VCC is equal to, let IB be the current here. If the current is IC and the total current is IE. VCC is IB RB plus base emitter voltage. So 10 volts IB base current, base resistance is 500 kilo ohms plus base emitter voltage is 0.7 volts. On calculation, base current is 18.6 microampere, 18.6 microamperes. Next, KVL at output side. VCC is equal to ICRC plus VCE. So 10. So given beta gain of transistor is 100. So common emitter configuration, gain beta is the ratio of output current to input current. Output current is IC, input current is IB. Now collector current IC is 100 times of base current, 100 into 18.6 micro, that is 10 power minus 6, that is 1.86 milliamperes. 1.86 milli 10 power minus 3, and collector resistance is 2 kilo ohms. 2 into 10 cube plus VCE. Now collector emitter voltage is 10 minus 3.72, so 6.28 volts. Quiescent point is VCE IC. So that is 6.28 volts, 1.86 milliamperes. This is Q point or bias point. So option 4 is correct. Next question. Given 4-bit counter, arrange the following counters in increasing order of their valid counts. Okay. So given n-bit counter, so that is 4-bit, here n is 4. So for n-bit ring counter, for n-bit ring counter, used states, unused states, used states and unused states. So for n-bit any counter, the total number of states will be 2 power n. So 2 power n is total states. For n-bit ring counter, there are n used states and 2 power n minus n are the unused states. Similarly, for twisted ring counter or Johnson counter or switched tail ring counter, it has 2 multiplied by n states, used states, and 2 power n minus 2n unused states. For mod 10 counter, used states are 10, that is 0 to 9, and unused states are 6. Next, for ripple counter, so total states are, all states are used, that is 2 power n minus 1, 0 to 2 power n minus 1. All states are used. So this is for ripple counter. All states are used, no unused states. So a ring counter with 4-bit ring counter has 4 used states. Johnson counter has 8 used states. Decade counter has 10 used states. That is from 0 to 9. And ring counter has 15 used states. Increasing order. So ripple counter has more number of states and ring counter has least number of states. So that is option C. So first one is least for ring. Next is twisted ring counter or Johnson counter. Followed by decade counter. And at last, highest count is for ripple counter. So option 3 is correct. Next question. So the frequencies used in satellite communication. For L band, these are the frequencies used in satellites band. Frequency bands used in satellite communications. C band is 4 gigahertz to 8 gigahertz. So 4 to 8 means C is 3. So that is 5.9 gigahertz to 6.4 gigahertz. Next is X band. So for X band, so this is X band. So for X band, 8 to 12 gigahertz, 8 gigahertz to 12 gigahertz. So 8 to 12 is 7.9 to 8.4. Now approximate option is B1. Next is KU band. For KU band, 12 to 18 gigahertz, 12 gigahertz to 18 gigahertz. So that is from the options 14 to 14.5 gigahertz. So C is 4 and KA band 27 to 27 gigahertz to, so it is 40 as per options 27 to 30 gigahertz. So that is D is 2, A3, B1, C4, D2. The correct option is 1. Next question. During oxidation process, which of the following statement is not correct? So they ask to find the incorrect statement. So 3 are correct, 1 is a wrong. Oxidation is a process. So we will see the definition of oxidation. Oxidation, it is a process by which the layer of silicon dioxide is grown on the surface of silicon wafer. So oxidation is a process by which a layer of silicon dioxide is grown on the surface of a silicon wafer. During oxidation process, silicon is consumed. Oxidation occurs at Si-SiO2 interface, not at the top of the oxide. During oxidation process, silicon is consumed. And oxidation occurs at silicon dioxide interface, not on the top of the oxide. Oxidation does not occur on the top of oxide. Next, so it is of two types. One is dry oxidation and wet oxidation. So this dry oxidation equation is Si plus O2, silicon oxygen gives rise to silicon dioxide. Wet oxidation, Si plus 2H2O gives rise to SiO2 plus 2H2. It is used to form, dry oxidation is used to form thin, highly controlled oxides. Thin and highly controlled oxides, whereas wet oxidation is used to form thick field oxides. The rate constant for wet oxidation of silicon increases with decrease in temperature. So this is wrong statement. Next, for the growth of an oxide of thickness D, so next, wet oxidation is governed by the equation Si plus 2H2O gives rise to SiO2 plus 2H2. Correct option. For the growth of an oxide of thickness D, a layer of silicon with a thickness of 0.44 D is consumed. So this statement is wrong. Next, during oxidation process, the SiO2 interface moves into the silicon. So this statement is correct. So here silicon interface moves into the silicon during oxidation process. If the temperature during oxidation is increased, the oxidation rate increases significantly both in wet and dry process. So here, with increase in temperature, the oxidation rate increases. Statement 1 is wrong. So option 1, 3 are wrong. Next question. Which of the following statement are correct? LDR, light dependent resistor, light dependent resistor, or photoresistor, or light activated resistor. The principle of operation is photoresistive effect or photoconductive effect. So LDR works on the principle of photoresistive effect or photoconductive effect. LDR when exposed to light, when light falls on a LDR or LDR when exposed to light, its resistance decreases and conductivity increases. So statement A is correct. LDR or light dependent resistors are based on photoconductive effect. LDR resistance decreases from dark resistance value with increase in light intensity. Statement B is wrong. Next, LDRs are slow responding to changes in light intensity. So the response time of LDR is slow. Response time of LDR is slow, especially in situation when light changes rapidly. So LDRs are known to have slow response time, react sluggishly to changes in light intensity. So LDRs have slow response time and or LDRs react sluggishly to changes in light intensity. Statement C is correct. Photodiodes are operated only in photoconductive region. It's wrong. Photodiode has two modes of operation. One is photovoltaic. It has two modes of operation. So one is photovoltaic and second one is photoconductive. So it is in reverse bias photovoltaic mode and no bias is applied. Statement D is wrong. Next, photodiodes have faster switching time when compared to phototransistor. So that statement is correct. Photodiodes are faster when compared to phototransistor. The phototransistors are slow. When compared between photodiodes and phototransistor, photodiodes are faster. Again in phototransistor, NPN phototransistor is faster compared to PNP phototransistor. So statement E is correct. So the correct option is A, C, E. A, C, E. Option 4 is correct. Next question. So closed loop non-inverting op amp, closed loop non-inverting op amp. In closed loop non-inverting operational amplifier, output voltage is sampled. Output voltage V0 is sampled and mixing with the input signal and mixing with input signal or input voltage. Output voltage V0 is sampled and mixes with the input signal, that is input voltage. So voltage sampling at output and voltage mixing at input. In this closed loop non-inverting amplifier, voltage sampling at output, voltage mixing at the input. So it is voltage series feedback. Voltage series feedback or series shunt topology. So voltage series feedback, it is also called voltage series feedback amplifier or series shunt topology. In voltage series feedback, input resistance Ri increases and output resistance R0 decreases. So for this voltage series feedback network or series shunt topology, in this case input resistance increases, output resistance decreases. Input resistance is increased, so statement C is correct. Next, one more example is common collector amplifier. Common collector amplifier is also an example for voltage series feedback. Bandwidth of non-inverting amplifier can be determined by using gain bandwidth product. So the bandwidth of non-inverting op amp can be determined by using gain bandwidth product. So gain bandwidth product, which is constant for a given op amp, so that is bandwidth is equal to gain bandwidth product multiplied by voltage gain AB. So in case of non-inverting closed loop operational amplifier, voltage gain is 1 plus Rf by R input resistance R1 or Ri if op amp is ideal. In case of inverting operational amplifier, voltage gain is minus Rf by R1 if op amp is ideal. Gain bandwidth of non-inverting operational amplifier is the gain bandwidth product multiplied by gain, that is 1 plus Rf by R1. This is the formula for bandwidth, and this gain bandwidth product is constant for op amp given in the op amp specifications. So statement A is wrong and statement B is wrong. The correct option is C, D. Statement C, D are correct. Correct option is 4. Next question. Arrange the following materials with respect to their thermal conductivity. So thermal conductivity K, it is a measure of material ability to conduct heat. Measure of material ability to conduct heat. And the units for thermal conductivity is watt per meter per Kelvin. Watt per meter Kelvin. Thermal conductivity is more for pure metals. It is highest in pure metals. Next, alloys, semiconductors, followed by dielectrics or non-metals or epoxy materials. So thermal conductivity K is highest for pure metals and K is lowest for dielectrics, non-metals and epoxies. Thermal conductivity K for silicon is 139. Silicon is a semiconductor. For silicon, thermal conductivity K is 139 watt per meter Kelvin, and for gold it is AU is gold, it is 315 watt per meter per Kelvin. For alumina 30, for epoxy or 0.14, for alumina 30, so therefore answer is alumina 30, epoxy 0.14. Correct option is 4. So B is the highest thermal conductivity. Gold has highest thermal conductivity, followed by alloys. Next is alloys is E, followed by semiconductors, that is A, silicon alloys, copper alloys. Next is semiconductors, silicon. Next is alumina, followed by epoxy. So correct option is D. Next question. It is related to signals and systems. Fourier transform properties. So time reversal. So the first one is time reversal. So time reversal. So if x of t has Fourier transform x of omega, then for x of minus t has Fourier transform of x of minus omega. Option 2. Reversal in time domain leads to reversal in frequency domain. Reversal in time domain leads to reversal in frequency domain. So A3. Next is time scaling. If the Fourier transform of x of t is x of omega, then time scaling Fourier transform of x of at is 1 by mod a capital X of omega by a. This is where a is any real constant. Time scaling property. Compression in time domain leads to spectral expansion, or expansion in time domain leads to spectral compression. Next, for next sum, so A is 3, for B it is 4. Next we will see the Fourier transforms for few signals. Fourier transform of delta of t is 1. Fourier transform of rectangular signal rect t is sinc function sinc f in frequency domain, or sinc omega by 2 pi. Fourier transform of triangular signal sinc square f, or sinc square omega by 2 pi. Fourier transform of e power minus at u of t is 1 by a plus j 2 pi f, or 1 by a plus j omega. Fourier transform of signum of t, signum function sgn is 1 by j pi f in frequency domain, or 2 by j omega. Fourier transform of t e power minus at u of t is 1 by a plus j 2 pi f square, or 1 by a plus j omega square. So C statement 1. Next is Fourier transform of real and odd signal is purely imaginary and odd. Odd signal Fourier transform of minus x of minus t. This is an odd signal, is minus x of minus f. So for D, it is 2. A3, B4, sorry, A3, B1, A3, B1, C4, A3, B1, C4, D2. So option 2 is correct. Next question. VTH, Thevenin's voltage, Thevenin's impedance, and short circuit current for the circuit given below. While calculating Thevenin's voltage VTH, all the impedance sources are replaced by internal resistance, and all the dependent voltage and current sources remain as it is. While calculating Thevenin's voltage VTH, all independent voltage sources are replaced by their internal resistances. Internal resistances and dependent voltage sources remain as it is. So independent voltage source is short circuited, independent current source is open circuited. So voltage source is short circuited, minus J4 ohm, J8 ohms, and this is 6 ohms. Now ZTH, for calculating equivalent impedance between open-ended terminals, ZTH is equivalent, this is open-ended terminal, between open-ended terminals. So ZTH is the 6 ohm parallel with J8 ohm, 6 ohm parallel to J8 ohm, and this 6 plus 8, 6 ohm plus 8 ohm parallel with this equivalence is in series with minus J 4 ohms. 6 ohm parallel with J8 ohm, and this is in series with minus J4 ohms. This is ZTH. So now ZTH on calculation, its value is 32 plus 24J, 6 plus 8J, or 4 at an angle of minus 16.261 ohms. So option C is correct. Next is open circuit voltage VTH. VTH is open circuit voltage. So this is open circuit voltage. So this is, here we have to calculate the voltage VTH. VTH is voltage across capacitor, say VA, and voltage across inductor, say VP. Now apply KVL in this loop. KVL for this loop. VTH is equal to VA plus VB. So voltage across capacitor A is 0 because current, there is no zero current is flowing across this element. So current I is 0 across the capacitor. Zero current is flowing through the capacitor. So VA is 0. Now VTH is voltage across inductor, that is VP. So VTH is VB J 8 ohms multiplied with 1 at angle of 30 source voltage Vs, and then total resistance is 6 plus 8J. 6 plus 8J. So 8J can be written as 8 at an angle of 90. 6 plus 8J can be written as 10 at an angle of 53.130. 8 at an angle of 90 multiplied with 8 at an angle of 30, sorry, 1 by 6 plus 8J, its value is 10 at angle of 53.13. So 8 at an angle of 120 by 10 at an angle of 53.13. So that is 0.8. Thevenin's voltage VTH is 0.8 at an angle of 66.8. Or we can directly say this thing. So option D is correct. Next is short circuit current. Short circuit current ISC is open circuit voltage by Thevenin's resistance ZTH. So that is 8 at an angle of 120, 6 plus 8J by ZTH 32, 24J, 6 plus 8J. So 8 at an angle of 120, 32 plus 24J, 8 at an angle of 120, 40 at an angle of 6.86. Its value is 0.2 at an angle of 83.13 ampere. This is short circuit current. 0.2 at an angle of, so this is wrong, A is wrong and B is wrong. So correct option is C, D, E are correct. C, D, E are correct. Option 3. Next question.